many sessions like book talks by Asha Vaste ma'am on sheltering angle and Mona Dr. Singhal ma'am from Auroville and so many different works and different discussions we have done so far. So today we will have a very interesting person, Nityam Jain. I will introduce him. Nityam Jain, he is a final year undergraduate student at SEP University. He is currently undertaking an internship at Kakani Associates, Ahmedabad. During his ninth semester, he assisted in the course of Advanced Structures, which is conducted by V.R. Shah, which is structural engineer, and Mangesh Belsare, architect. The course focused on building fundamental understanding of structural systems essential for architectural design, emphasizing an integrated approach where structure is not treated as an afterthought but as a critical element that informs spatial organization and vice versa. Uh, in the curriculum, it involved detailed case studies of master architects and engineers such as Enzo Piano, Norman Foster, and Eladio Dieste, examining how structural systems and architectural expression evolve in response to each other. Yeah, so we are excited to have you, Nityam, and it's yeah,
Thank you. Thank you, Ashwin. Uh, I'll just start screen sharing my. I've just made a PPT and I'll just share and like talk about it. Give me. Can you guys see it?
yeah, your screen is visible, Nityam.
Yeah, yeah, yeah. If it's okay for other people to turn on their cameras, I can also understand how it's how it's going. So if possible. Mhm. Yeah. So my introduction, I think Harshvardhan already gave. So I'm a final year student, and last semester I was a teaching assistant in this course. So which is why I'm here. It's called advanced structures. It's not like very advanced concepts
Nityam,
of
sorry,
structures or like heavy technical. Yeah.
yeah, sorry to disturb you. Can you just minimize or drop it down that screen of Meet so that student can see the presentation complete?
Okay, that is also visible.
Yeah,
Yeah.
yeah, thanks.
Now it's fine, I guess.
Yeah, perfect, perfect.
This also I can. Yeah. Uh, yeah. So it's based on like the whole presentation is taken from this, and basically I'll just I'll just brief them because most of it is taken from the course, and these are not my like understanding, like not my work, most of it. And I've like most of the time I might code them as I've done like a lot of courses with Vyasha and Mangesh, like around three with Vyasha and eight courses with Mangesh. So I just wanted to give them the credit. If you don't know Vyasha, he's the structural engineer behind the new Nalanda University that's upcoming in Bihar, and also the Smriti Earthquake Memorial, everyone would have seen, I guess. So he's the person behind all of this. And so basically, first I'll take you guys through what we did and in the course and what I contributed as a teaching assistant. So first, like this is just a 12-week course, and we just made a chart on what all topics were covered. So to make a sort of checklist for students as like to remember concepts and for us as well as what should be covered, what extra can be done, etc. So these were the topics covered in the 12 weeks. And the main objective of the course was to fill the gap between the architect and the structural engineer. So the architects don't have to struggle while negotiating with engineers after they made some design. And they can also, like mostly conceptually, they can design the structure. And the structural engineer just have to give sizes and not negotiate the whole design and the addition of extra members or something like that. So it's mainly to teach these concepts. And as I said, these concepts are very fundamental, as in like understanding bending, buckling, the depth, or earthquake forces. And then because all of these fundamental concepts work together in unison, it becomes an advanced concept. That's why it was a 4th year course. And just it's not about calculations, it's just about the relationship between numbers and concepts, which help the architect uh, express the structure in a different way, not to exactly calculate and everything. So this was just a simple timeline of the assignments we had designed for the students, which concluded in the final assignment, which I'll be showing. So most of this, like all of this is done by the junior batch, 1 year junior to me. So I've given the credits. So we started with a small architect background study. And one of the main things about the courses is it has to be heavily graphical. It can't be word like text heavy because as architects, we should know how to express ourselves in drawings or in graphics and not with words or heavy word document sort of files for these kind of assignments. So these were just to study the language of the architect or the material they use or which region or which timeline they belong to, something or what forms, what elements do they use predominantly, something like that. And then all of them were given one building, and they were not given, they were given a specific architect, some architect who works with these kind of forms and structural systems, and which had enough scope to study on. Architects like Richard Rogers, Norman Foster, Eladio Dieste, Grimshaw architects, or even structural engineers like Pierluigi Nervi, Robert Maillard, Buckminster Fuller, and on their projects, people had to select buildings, and then we approved which is good enough for studying or which doesn't have that much scope. And thus they went ahead with the case studies. And they were supposed to keep analyzing the buildings as the concepts were taught in the class. So these are some of the assignments which were also given like a graphical summary sort of way, as in what is the concept, where is the concept seen in your building. So these are just like some of the student assignments. I'll just like slide through it. They were also told to make the model of the existing building in the minimal sizes of the boards. So it's not a visual model of how the building looks, but it's just a structural model. And because the board and the material is so thin and flimsy, when you put the gravitation load or the lateral loads or uh, give it jerks like the earthquake load, you should be able to see the deformation it's going through, where the bending is happening, where tension is there, the threads might get tighter or they might get looser. So you understand what failure might happen to the building on these kind of loads. So maybe it will help you understand the building or understand the specific role of each part of the building. And again, some other building. And then this were like analyzing, students were analyzing how and what is happening. And it led to the main final sort of exercise where the aim is to make the same building retain the scale and proportion and the functionality of the building, but then change the structural system of it. Like someone can decide to make a steel building into a concrete building. That will change the thickness, the spatial qualities, the details of it, of how the joints will be, how thick will it be. So the whole expression of the space changes, but still keeping in mind the span, what is the function of the space, like extra columns shouldn't be there, that much span should be possible. So this was one of the most interesting exercises I find. Even when I did the course, this was like my favorite. Even this building by Norman Foster. So how the same thing can be done in castellated beams, but it's sort of arched here. So like it's possible with just a beam also. And the process was repeated again to like sort of make different iterations and not just make like another form, but like try different. So here, this person tried converting Hutch terminus, which is a tensile structure, into a ferroconcrete structure, which he made it into a dome sort of thing. So here, like they are supposed to learn how it's not a technical requirement for which the structure came. The structure came because of the spatial requirements and what the space required. And there are obviously multiple ways to do the single thing of putting a roof or a shelter to this space. But like it's the architect intentional choice of how you want to express it. Do you want like a heavy concrete shell which gives more enclosure? Do you want a light translucent canvas sheet over the building? So this was the point of this exercise. And something we added for the first time was like a reel of the learnings. So to sort of go with the newer mediums that are coming up and how people engage with these kind of things, we saw some things like on Instagram, and then we got inspired by it. Like, why not make it and then upload it to maybe the general public can see it, comment. We can also understand if we have understood everything. And this way, we could also check if students have understood things and how good they can communicate the whole learning of the semester into a 1 minute video. So I'll just open the page. I'll also share the username so other people can go through it on their own time. But I'll just open some of it just to just put it here so if anyone wants to take a look later, the whole batches videos here. So, yeah. So this was the course, and now one last thing we also added was to actually see how much people grasp. In SEPT, we usually do not take exams. It's mostly dependent on the assignment, but because of the increasing use of AI and like one doesn't understand if people have actually understood things or just made AI do it. So me and the other TA, we designed a simple and fast exam of MCQs true and false, which people were supposed to do in 1 hour, and then we made everyone sit apart and we could actually understand. And there were some unexpected highs and lows which came up because we cannot understand the learnings through only assignments. So this was something new we started, and now I'll just go through like some concepts, the two main concepts which I think were the main in for us to design spaces and how to the like only the concepts that govern architectural expression of like the same thing can happen in different ways. So I'll just go through two concepts which I've taken and just feel free to ask doubts because it was a little hard to understand of like on the level where I should start and make this PPT. So just anyone can pause me if it's getting too basic or if I should cover anything else. So just to fill any gaps and clear uh, any doubts, I just want to like the basic things. There's compression, tension, which are called as the axial forces because they act along the axis and they allow like the maximum use of the material instead of what we see in bending where the top member goes in compression and bottom tension, and this happens because of across forces because it's perpendicular to the axis of the length of the member. So bending is also called as the least efficient way of uh, make of transferring the loads. And if one understands that like the top member is under compression, bottom under tension, one can express the same beam as a compressive member on the top and a tension cable at the bottoms to reduce the member sizes as well. Or if we see like in a section of the beam, uh, like a diagram of the section of the beam, and if we see the forces at the top, there's maximum compression, at the bottom, there's maximum tension. So approx in the middle, like the material is just dead load and redundant. So one can take that understanding and create something like a castellated beam. Like these are some things which I think everyone would know, but just like covering up on how people can express, like take a concept and how they can express it in the structure, and how the same bending member can be changed into a truss. So changing across forces into axial forces makes it more lighter, and even now the forces are transferred in a much more efficient way because it's only axial forces now. The bending has been converted into tension and compression, pure forces. And if we see that happens because of triangulation, when you put force on any vertex of a triangle, you get compression in some, tension in some. Buckling, which happens only because of axial forces, which is why buckling and bending shouldn't be mistaken with each other because bending happens because of perpendicular forces. Moving to the first concept, let's just take a look at these structures, which and think if there's anything common between them. So first is Salginatobel Bridge by Robert Maillard, who is an engineer. Just to give a sense of scale of the bridge. And Sydney Harbour Bridge, this is also by a engineer, not any architect. And also Eiffel Tower. So if we see any common link between these structures, like the form of the structural system could have been anything, like here we see triangulated trusses, but here we see solid monolithic concrete which has been made into a long spanning bridge. So if we see the forms, it's sort of similar because it is derived from the bending moment. So basically, if anyone doesn't know, bending moment is the the exact formula would be the force multiplied by the distance between the point B where we want to calculate the moment was in and this. So the bending moment here would be forced into the displacement between point A and point B. A would be like where the force is acting. Or in simple terms, it is the stress acting upon the structural member at the given point in the given moment. So this definition leads to a diagram which basically helps one to understand. If we dissect both of these structures, and if we see a normal cantilever beam and the bending moment diagram of a cantilever beam, so it's exactly like this. The plus and minus are just sort of to show it graphically. The plus is when the beam or the member sags, and minus is when it hogs. So basically, if we imagine the deformation, it would be something like this. So instead of bending like a normal beam, it sags, which is why the bending moment goes in negative. So if we just take this diagram, mirror it, and then we can see the bridge is like literally there, which also emerged because of the issue where this valley was so deep where they couldn't make any formwork or add any column in the middle. So they started building from both the sides, and then it's not a exactly like a spanning member, but it becomes like two cantilever beams just touching in the middle. So even if it looks like a normal beam, it becomes two individual members, which is acting like that and even designed like that. If we just imagine it like a cantilever from the ground, like a vertical cantilever, the same thing, if we mirror it, we almost get the form of the Eiffel Tower, which for how it's derived because, like, if it's a cantilever, there would be lateral forces of winds and everything acting on it. So to tackle that, it's made as a diagram of the bending moment. Similarly, if you see a fixed beam, which is properly tied on both the sides, let's say like a concrete beam. So if we see the bending moment of that, it comes somewhat like this, where it hogs a little in the corners because of the fixed condition. If we want to imagine the deformation, could be something like this. So just where it hogs, negative, where it sags, positive. So the bending moment comes like this. And another interesting thing is it's always a parabola. So like if we take this thing, it fully represents of how the Sydney Harbour Bridge is here. So it's like exactly made from the diagram of a fixed beam, and this arch is made which like supports the bridge from individual ties. So this is how like it was derived. If we take similarly like a simply supported beam, like let's say a wooden beam, so for it, bending moment diagram sort of comes like this, and even the deformation exactly is like this. So these kind of bridges, a lot of people would have seen because if you take a rolling wheel joint, which is given in like highways and huge flyovers. So that acts like a simply supported beam. And when people make bridges there, it sort of uh, looks like this. It's just a random bridge taken from the internet. But these bridges are usually made when the condition is like this, like the simply supported beam. So that's how the form emerges. Another main concept that they teach is type of joints. It's not something like I think this it's there in like one or two books. I can share it later if anyone is interested. But basically, it's a concept of seeing structure. So there are mainly two kinds of joints. A rigid joint, it's represented like this, a pin joint. And if like a member makes a rigid joint with the ground, it's called fix. If it's a pin joined with the ground, it's called hinge. And basically, a pin just acts like a literal pin where it can rotate or move along it. And rigid and fixed are just like a monolithic concrete sort of thing where it cannot rotate or move. So just to visualize it, this becomes like a rigid joint where nothing is allowed, no movement is allowed, something like this as well. But this is like a literal pin joint where things can move and rotate as well. This is the detail from Pompidou Center. So basically, like in fixed joint, no rotation, no vertical movement, no horizontal movement. And if we take a simply supported beam or like pin joints here, then the deformation can be sort of like this. And if we like, let's just say in a structure, if you have two pin joints and two hinge joints, so like that is the limit of any structure. Like there cannot be more than three pin joints, or like I'm just generalizing hinge as pins here. So if lateral forces come, the uh, rectangle will just make into a parallelogram. So that is one of the concepts that the collapse mechanism of any structure is three pin. You cannot like whenever there are earthquakes or like huge forces that come on any structure, and if you have cracks forming on the beams, so in any beam, the maximum cracks it can form is three. When the fourth one comes, it's like sort of acts like a pin joint because like it can basically rotate or move from the crack. So at that point, the building can collapse, which like you can visualize from this. And thus, just to visualize like how a three pin system can also be stable, let's just say these are like one, two, and three pins, and this is like a rigid structure, like let's say a steel L member. So how these two would want to rotate is in this circle, and how it would want to rotate is in this circle. So this point can only exist like here, like thus the left or the right member cannot rotate in any way. So even if it does seem like how like these three little pin joints can be stable, this is how one can visualize like no movement is allowed, even though if there are pin joints. And this is like sort of seen in the first bridge that I showed, Saljina Tobel bridge. And just to see like in a triangle, usually if you have three pin joints, there can be no movement because like it cannot form a parallelogram. Basically, a triangle cannot be deformed. It's the strongest form. And on that logic, triangulation allows like what I was saying, bending into like pure axial forces. And it's not like in any truss, as like I'm saying, it can be pin joints. In any truss, you would have seen like all of the steel is welded together, but conceptually they act like pin joints because the member sizes are so small that when the loads act, it can literally rotate a little bit. Like just imagine having a thin steel wire in your hand and like you want to bend it. So it would kind of act like that. It's not a little pin which is there, but then that bending allows like a pin joint sort of behavior. So which is why it gets sort of confusing for people because people think like only a little pin which they see in those kind of details that I showed earlier is only like the pin joint, but it's the behavior that they teach in the course which one has to like visualize and figure out in like the buildings they're given. Let's take this example. Let's say this is like a canopy sort of thing. So because the member is so thin at the bottom, this can happen. So basically here we can say the bottom is acting like a pin joint, not like a fixed joint. Even if it's welded to the ground or bolted to the ground, it doesn't matter. The thin member profile allows that pin behavior, which will lead the canopy to do this, or like a cantilever, if we see, it might do this. Or even if it is a literal pin joint, like the detail that I showed, if it's triangulated with like other members or other tension cable or rods, if you imagine, that same thing because of triangulation will become a fixed joint as a whole. So even if you're seeing like it's a pin joint, as a whole, it's going to act like a fixed joint. So that is what people have to figure out and then see if it's like a 3-pin system, a 2-pin system, or what can be the different ways it can be expressed. So if we have something like this, it can be added infinitely to make it a stable structure. This concept is just a diagram from FLW's Johnson wax. So basically, how they have like a very thin member size at the bottom, and these are just touching at the top. So like all of these canopies just support each other, and if we take only two in isolation, sort of act like a 3-pin system, how I showed earlier. So when you add these in 2D and 3D, it just becomes stable instead of what would happen with just one. So, like here, if you know that the bottom can be expressed like a pin, one can make it a little pin joint of how I showed, or it can become like the minimum thickness that you want it to be. It doesn't have to be a thick cylindrical member that goes through the space. So that is what students had to do of how you can figure it out. And the top, where it's meeting the horizontal plate, that has to be a fixed, rigid member. Thus, you cannot have like a thin profile there. You have to make it broader just to have more strength there. Another example by Eladio Dieste, Cristo Obrero Church. So it's made from reinforced bricks, a very interesting structure. So here, if we see the section, the wall at the bottom is like a straight wall, and at the top it becomes like a corrugation, which provides more stiffness. But while it was getting constructed, they had given it support because the individual walls cannot stand. It's just going to act like a like if you want to visualize a bed which is kept, it will just collapse. So it just acts like that. And in principle, now the bottom of the wall act like the pin joint, which I was saying, and the top, because of the corrugations and the connection it will make from the roof, it becomes a fixed joint. So now, as a system, it's stable because there are only two pin joints, and there is no rotation allowed. Even if there's rotation allowed at the bottom, as a system, no deformation can happen. So because of this understanding, one can like literally have this thin uh, member at the bottom, and still it can be stable. So these sort of things were there. If we take a look at Pompidou Center by Richard Rogers and Norman Foster, uh, Renzo Piano as well. In this section, like the span is approx 48 meters, And how they had designed it was, now we have this huge span which is going to bend very easily. So they added these extra members which will also